Hello all, welcome back to Operations Research 2 course. We are considering the network models. In our previous lectures, we learned fundamentals of network models. We learned minimal spanning tree and shortest path problems, and we learned how to formulate maximal flow problems as linear programming formulations. And in this lecture, we will learn how to formulate the shortest path problem and the minimum cost network flow problems, similar to maximal flow problems. So let's get started. Remember, in our previous lectures, we learned how to solve shortest path or shortest route problems using the Dijkstra's algorithm, or as sometimes it is pronounced, Dijkstra's algorithm. And in the shortest path problem, the objective is to determine the shortest route between any two nodes on a given network. So the starting node can be S and the final node can be T, and we want to find the shortest path from node S to T. Okay, so how can we formulate this problem? And in order to formulate it, actually, we will assume that on this network, one unit of flow enters into the network at node S, which is the starting node, and we will assume that this 1 unit of flow will leave the network at node T. Okay, so since there is a 1 unit of flow, then this 1 unit or the flow that is passing through the arcs will represent the shortest path from the source to the sink or the final node. And the rest of the formulation, in fact, is similar to what we did in maximal flow problems. We will represent our decision variable as xij, which will be amount of flow in arc ij. But there is one restriction here. This amount of flow in the maximal flow problems, they could take any values. They could be integer values, or they could take decimals as well. For example, 2.5 units of flow is possible. But in the shortest path, this problem, actually we are formulating it similar to a maximal flow problem, but in fact we are not dealing with the amount of flow. We consider whether an arc is on the shortest path or not. So if a flow passes through an arc, we will assume that it is on the shortest path, otherwise it is not. And for this reason, we shouldn't allow a flow of, let's say, 0.1, 0.5. The amount of flow that enters into the system is only 1. So it means that this 1 unit should travel through the arcs without further dividing into smaller parts, and should exit from this final node, terminal node. Therefore, in this formulation, our decision variable xij will not be a regular continuous decision variable, but in fact we will assume it to be take values 1 or 0. If it takes the value of 1, it means that this arc ij is on the shortest path, and if it is 0, this arc is not used on the shortest path. And the Cij, with Cij, we will represent the length of arc ij. Actually, this is different from a maximal flow problem, because in the maximal flow we want to maximize the total amount that we are sending from source to the sink. But here we will try to minimize the total distance, and the total distance will be calculated by using the length of the arcs. So our objective function is also a little bit different from the maximal flow problems. So this xij now represents the amount of flow which can take only values 0 or 1, and this cij is the length of arc which is given, which is the problem parameter, and we will use it in the objective function. And how do we write our objective function? It is a minimization problem. We try to minimize the total distance, and the total distance will be defined as the length of the arc multiplied by this decision variable, which represents the amount of flow, which actually takes values 0 or 1, and this is among all arcs on the network. So we will multiply the length with xij for all arcs on the network. And then the constraints is basically we will write the flow conservation constraints. And this simply says that total flow into a node should be equal to the total flow out of that node. Okay, this is the flow balance constraints or conservation of flow constraints, the same thing. So for each node, let's consider node J. If there is an external input into that node J, so let me write it like this. So we will see some other examples of this. Let's say this is node J. And for this node J, let's assume that there are other nodes, for example, node I, node K, and etc. So from these other nodes, there can be some inflows. And also this in this node J, in maximal or in min cost network flow problems, we will see there can be some production. If it is a maximal flow, there can be some production or some supply amount that is satisfied from this node J. So it's not coming through another node, but it's generated in this node, for example, 10 units. So we add all the amount of flow that are coming through other nodes plus any additional external input, and this should be equal to all amount of outflow from this node J. Let's say this is node K, this is other nodes, and etc. So all output to all these nodes, plus maybe in some nodes there can be some demands, so they consume, the node itself consumes some amount, let's say 15 units. So it's not going to other nodes, but it's used in this node J. So this is the external output from node J. Okay, so this flow balance constraint simply says that this equality should be satisfied for all nodes. And let's consider this simple example to formulate the shortest path problem. Okay, so assume we want to determine the shortest route from node 1 to node 2. So this is the starting point, node 1, and this is the final or terminating node, node 2. Of course, this is a very small example. You can just observe and find the shortest path to be, for example, I guess it is this one. Go from 1 to 3 and 3 to 4 and 4 to 2, and the total distance will be 30 plus 10 plus 15, so it will be 55 units. Okay, this is the shortest distance. But our objective here is not to solve, because we can solve it using the Dijkstra's algorithm. Our objective here is to formulate this problem. And how to start the formulating the problem? Simply, as I explained in the previous slide, we will assume that in the source node, in the starting node, we will assume that there is a 1 unit of inflow into the network. Okay, so this 1 unit represents the amount of input. And in the terminating node, in the final node, we assume that there is a 1 unit of outflow. Okay, now with this inflow and outflow that we defined in the starting node and in the final node, we will write the objective function and the flow balance constraints or flow conservation constraints, and when we implement it in Cplex OPL, we will find the shortest path. So let's consider this network now. How do we write the objective function? Remember, the objective function says that we should multiply Cij, which was the distance of arc ij, with xij, and we should do this for all arcs ij that are defined in the network. So the arcs defined in the network are these. For example, this arc 1, 2, it is defined. Arc 1, 3, it is defined. But look, there is no arc 1, 4. This arc is not defined. So we write the objective function only for the arcs that are defined in this network. So the first one, x12, what is the distance? It's 100. 100 times x12. Then x13, the distance is 30 times x13. And we continue 20 times x23. Okay, so let me write it, 20 times x23 plus what else? 10 times x34 plus 60 times x35, 60 times x35. Remember, this is a directed arc, and it means that x35 is not equal to x53. It is different. This 35 says that the arc starts from node 3 and moves to node 5. Okay, so it is not the same thing. This is just a remark. 60 times x35, and then what else? We have 15 times x42 plus we have this 50 times x45, which is this one. So this is our objective function. And what about the constraints? Conservation of flow constraints we need to write. And what are the conservation of flow constraints? For each node, the total input should be equal to the total output. And now look, for this node 1, let's try to write it. In this node 1, this 1 is an external input. It is not coming through another node. It's an external input. And our flow balance constraint says that any input into node 1, whether it's coming from another node or from, if it is an external input, this amount of input to node 1, and there are no others, this 1 should be equal to the output. And the output is x12, either this one or x13, or this one. So for node 1, the flow balance constraint is this. For node 2, now look, the input into node 2 is x12 and x42. So x12 plus x42 is equal to the output, and the output can be x23 or this external output. It's not going to another node, but it is the output of this. So x23 plus 1. Similarly, we do the same thing for all nodes, node 3, 4, 5, for all of them we write these flow balance constraints. For node 3, input, the amount of input is 1, 3 plus 2, 3, and the output is 3, 4 and 3, 5. Okay, 1, 3, 2, 3 equal to 3, 4, 3, 5. And for node 4, the input is this one and the output are these two. And for node 5, there is only input but no output, as you can see. Okay, now these are the flow balance constraints, and we can represent this in a table. But remember, when we represent these in a table, we said that we will keep the decision variables on the left hand side and the constraints, the constants on the right hand side. So we can represent this first one as, instead of writing this on this side, we can just simply say that it's equal to 1. And look, in this one, we can move this x23 to this side and represent this as x12 plus x42 minus x23 equal to 1. And this is correct, nothing wrong. But now, as you can see, this right hand side is equal to 1 and this right hand side is equal to 1. And if you look, the first one is an input into a node and the second one is an output from that node. And if we write both right hand side as equal to 1, we will not understand which one is an input and which one is an output, or in this case of shortest path problem, we will not understand which one is the starting node and which one is the terminating or final node. And in order to make it clear, we will assume that an inflow into a node, the right hand side will always be positive, but if it's an outflow, this amount, then we will assume that the right hand side is a negative value. But we cannot simply write it here -1. It is not correct. What we will do is actually on this equation here, this equation, instead of moving this x23 to this side, instead I will move this part to this side and I will move this 1 to the left hand side. Okay, and then what we will have? We will have minus x12 minus x42 plus x23 equal to -1. Okay, so this will be the representation for this node. Let me repeat. The version, whichever you write it, is, correct. There is no mistake when you write this one by just moving this decision variable to left hand side and keeping this one on the right hand side. It's correct. It's not wrong. But in order to understand that this, for this node 1, it is the starting node and this node 2 is the terminating one. For node 1, there is an inflow of 1 unit. We will represent it as plus. And for node 2, since it's an outflow, then we will write the equation in a way that this 1 is a -1. Okay? And again, for the other nodes, we will move the decision variables on one hand side so that the right hand sides will be 0. So this is how we represent the shortest path problem, similar to the maximal flow problem, as a table. So we have this objective function, and look, now the objective function, different than the maximal flow problems, we write the distances of the arcs here. And the objective function is simply 100 times x12 plus 30 times x13 plus 20 times x23 and etc. Okay, so we have written all these distances into these tables. Again, we have a row for each node, including the starting and the terminating one. In maximal flow, remember, we have written the flow balance constraints only, not including the source and the sink, but in the shortest path, we write for all of them. Okay, and then at each node, in node 1, we say that x12, this is the outflow, and x13, this is the outflow, is equal to 1, which is the input into this constraint. For node 2, on the other hand, since it is the final node, we want to find the shortest path from node 1 to node 2. Therefore, the right-hand side of node 2, I'm writing it as a -1. So it means that x12 minus x12 minus x42 equal to x23. Plus x23 equal to -1. And for all other constraints, the right-hand side are 0. Okay, so in maximal flow problems, remember, all the right-hand sides were 0. But here, the right-hand sides for the shortest path problem, are equal to +1 and -1 for the starting and terminating nodes and 0 for all others. Okay, now for node 3, look, how do we write? x13, but minus x13 minus x23, these are the inflow, is equal to x34 plus x34 plus x35 equal to 0. Okay, now if you like, you can just multiply this row by -1, and what will happen? This will be +1, this will be +1, this will be -1, this will be -1, and the right hand side will still be 0, and this is also correct. Okay, it's not a problem, but it's better to be consistent by while writing all of these. And while writing all of these, we assume that in the shortest path problem, we assume that all inflow is negative. So x13, x23, all inflow is negative and all outflow is positive. Again, in node 2, look, this is inflow and this is outflow. We assume inflow is negative and outflow is positive, but as I told you, it doesn't make a change. It is not wrong if you multiply each row by -1. When we implement this formulation in Cplex OPL, we can find the optimal solution to be x13 equal to 1. What does it mean? It says that this arc is on the shortest path. And it says that x34 is equal to 1. It means that this arc is on the shortest path. And x42 equal to 1, which says that this arc is also on the shortest path. And the objective function appears to be 55, which is equal to 30 plus 10 plus 15. Okay, so this is the shortest route with distance 55 miles. And if you remember in our previous table, for node 5, we have this inflow, and inflow is x35 plus x45. And what is the outflow? Outflow is 0. Okay, total inflow should be equal to total outflow, and there's no outflow here. And this implies that x35 and x45 are equal to 0. They cannot take any positive values because we know all xij should be greater than or equal to 0. Okay, so it means that actually you don't need to consider this x35 and x45 in your LP. They will already be 0. Of course, when you write it, the result will not be wrong, but it's unnecessary. You don't need to write these into your formulation. Okay, now let's consider this example problem, and let's develop the LP model to determine the shortest route from this node 3 to node 7. Okay, node 3 to node 7. So how do we start? We say that, okay, this input, the starting node, node 3, we say that there's an external flow of 1 unit, and for the final node, terminating node, we assume that there will be an outflow of 1 unit. And then we will construct the table. So when you have the table, you already have the formulation. You don't need to write the formulation in all the details. Okay, so in our formulation, we will have a row for the objective function and for all the constraints, for all the nodes, and we will have a column for all the arcs, and we will have a column for the right hand side. Okay, so first let's write the objective function. The objective function is the distance times the decision variable. So for the first arc x12, the distance is 1 unit, so it will be 1 times x12. For the second one, it's 2 times x13. For 23, it's 1 times x23. Then for 24, it is 5 times x24 and 2 times x25. and for x34 it is 2 times x34, 1 times x35, 4 times x36, then 3 times x45, then 6 times x46, 8 times x47, 7 times 3 times x56, 7 times x57, 5 x67, 2 x68, and 6 x78. This is our objective function that we want to minimize. Now our constraints. We need to write all these flow balance constraints for all nodes. So node 1, it says that the inflow should be equal to outflow, and we will write the inflow as positive and outflow as negative. So for node 1 there is no inflow, okay, only outflow. So the outflow value x13, so x13 will be inflow will be negative and the outflow will be positive, and the outflow for node 1 for x13, okay, this is an outflow, and x12 is also an outflow, and there is no inflow, and the right hand side will be equal to 0 then. And again, a similar observation, this constraint says that x12 plus x13 equals to 0, and simply you can just delete these decision variables from your model and don't consider it at all, and you will obtain the correct solution. But here we are going to write all of them, no problem. For node 2, okay, by the way, there was a 1 unit inflow to node 3, starting node, and this is the final destination node. Okay, for node 2, the inflow is 1, 2, so it is -1, and the outflow is 2, 3, 2, 4, and 2, 5, and this should be equal to 0. For node 3, so since it is the starting one, the right hand side will be equal to 1, and this should be equal to and also there are some inflow, as you can see, 2, 3, so it will be -1, and then 1, 3, this should also be -1, so the total inflow, this one plus this one, should be equal to the outflow, which is x34, x35, and x36, okay, this one, and this one. Now for node 4, let's consider node 4, which is this one. The total inflow, it is 2, 4, x24, and 3, 4, this one, should be equal to the outflow, which is x45, 46, and 47, and this should be equal to 0. For node 5, the inflow x25, so it is -1, x35, it is -1, x45 also, and then x56, 57 are the outflow, and this should be equal to 0. For node 6, inflow, okay, x36, x46, and 56, and the outflow is x67 and 8, and this should be 0. Okay, for 7, this is the destination, and for destination, the right hand side, I will write -1, this one. So the inflow x47, 57, and 67, and the outflow is x78. And for node 8, the inflow x68 and 78, and this will be equal to the outflow, but the outflow is 0. And again, similar to our previous discussion, x68 plus x78 is equal to 0 for node 8, and the total inflow should be equal to outflow. And because of this, x68 and 78 will always be 0. So you can delete these from your model and just write the model for the rest. And this is our shortest route formulation for this example problem. Another important model or problem in network models is the minimum cost network flow problems. These problems are very general problems, and what we try to do is, given a network, we try to determine the minimum cost flow from the supply points to these demand points to satisfy all the demand from the supplies by considering the capacity restrictions on arcs. So the arcs have their costs, their capacities, and these capacities can be lower limits and upper limits, we will talk. And we want to satisfy all the demand at different nodes, so that how can we satisfy these demands? By satisfying the capacity restrictions with minimum cost. Okay, and the thing is, the problems that we have already seen, the transportation problem is a special case of a minimum cost network flow problem. We already know that assignment problem is a special case of the transportation problem, and this is a special case of minimum cost network flow problems, which means that assignment problem is also a special case of minimum cost network flow problems. We haven't seen these transshipment problems in this course, but it is also a special case of the minimum cost network flows. Shortest path problems, maximum flow problems are also special versions of minimum cost network flows. And the critical path method that we will see in the next lecture is also a special case of the minimum cost network flow. So minimum cost network flow problems are the most general type of network flow problems. And with this example, let me try to explain what we try to do. So on this network here, as you can see, there are nodes and arcs between, and some of the nodes, as you can see, have a positive number written beside them, which means that this node has a supply amount of 20 units. In some of the nodes, as you can see, we don't have these numbers, so they don't supply anything. But in some of the nodes, as you can see, we have some negative numbers. These negative numbers represent the demand value at these nodes. Okay, so this node 4 demands 5 units, and node 5 demands 15 units, and node 1 has a supply amount of 20 units. And node 2 and 3 does not supply anything, and do not demand anything at all. And when we look at the total supply on the network, the total supply is only from this node 1, which is 20. And when we look at the total demand, which are nodes 4 and 5, the total demand is equal to total supply, which means that we can find a feasible solution to this problem. Similar to the transportation problem, right? This is a balanced problem. And on the other hand, on the arcs, if you look, we have these numbers over here. This second number, which is $4, it is the transportation cost of transporting 1 unit of flow from node 1 to node 2. Okay, this is the cost. And the second number over here is the capacity of this arc. This is the upper capacity in this example. It is the upper capacity. So it means that you cannot send more than 15 units from node 1 to 2. In some cases, we have both a lower capacity and an upper capacity. We represent the lower capacity with Lij and the upper capacity with Uij. And this Lij, for example, if it is between 5 and 50, it says that you have to send at least 5 units. At least, it cannot be less than 5. And you can send at most 50 units. So it cannot be more than 50. Okay, so we may have such capacity restrictions on the arcs. And we can denote these with different parameters and decision variables, similar to the shortest path and maximal flow problems. Our decision variable xij will be the amount of flow or the number of units of flow sent from node I to node j through this arc ij. Okay, the same decision variable definition. But this time we have some additional parameters which is different than the maximal flow problem. So this Bi will be the net supply, which is the outflow minus inflow at node I. Look, at this node 1, the net supply amount is 20. Okay, but in this node 4, the net supply is minus 5. And in this node 5, the net supply amount is minus 15. So this Bi can be positive or negative. If it is positive, it means that it is a supply amount. If it is negative, it means that it is a demand amount. And this Cij is the cost of transporting 1 unit of flow on this arc. So this $4 for arc 1, 2, $2 for arc 2, 3. By the way, as you can see, this arc has an upper limit of infinity, upper capacity. It means that actually there is no capacity limit on this arc. But on some others, we have such capacity limits. And as I explained, this Lij is the lower bound or the lower limit on arc ij. And if there is no lower bound, then it means that this Lij is 0. And in this example, all Lij are 0. That's why they are not written here. All of them are 0. And Uij is the upper capacity on arc ij, upper limit. Sometimes we call it upper bound. And on some arcs, as you can see, there are no upper bounds. We represent them by setting this Uij equal to infinity. Now, how do we formulate these problems? Actually, the formulation is very simple. We simply minimize the total cost of flow. So this version is very similar to shortest path, remember. But in the shortest path problem, we formulated this Cij represented the distance. But in this problem, it is the cost. Okay? The cost multiplied by xij. For example, for this one, it's 4 times x12 plus this one 4 times x13 plus this one 2 times x23 and etc. All of them for all the arcs on the network. And for each node I in the network, we write these flow balance constraints. So this is conservation of flow or flow balance, the same thing, conservation of flow constraints. And look at this node 1. The amount of supply in node 1 is equal to 20. So the right hand side is equal to 20. So what do we write? Outflow minus inflow. Okay, so outflow from node 1 is x12 plus x13. This is the outflow minus inflow into node I. Okay, and for node 1 there are no inflow. And simply for node 1 we write this. Outflow should be equal to 20. But have a look at node 2. Okay, in node 2, let me write it here. Node 2. What is the outflow? It can be 2, 3, 2, 4, and 2, 5. So x 2, 3 plus 2, 4 plus 2, 5. minus what's inflow, it's x12, and this will be equal to BI, the net supply. And what is supply amount in node 2? There is no supply, there is no demand, so it is 0. Okay, so if there is a supply or demand, then we write it on the right hand side, but if there is no supply or demand, the right hand side will be 0. So let me write this constraint also for node 4, and it can be more clear. For node 4, how do we write? The outflow from this node 4 is x45 minus inflow 24 and 34, and this will be equal to net supply amount, and net supply is -5. It means that it is a demand. Okay, so for node 4 our constraint will be like this, and these are the flow balance constraints. And finally we have the arc capacity constraints, and it means that the flow on each arc should be greater than or equal to the lower bound and less than or equal to the upper bound. For example, let me clear this part a little bit, and for example, for arc 1, 2, we don't have a lower limit, but we just have an upper limit. So it simply says that x12 is less than or equal to 15, and the lower limit is simply 0. Okay, so you don't need to write this part over here, only this is satisfactory, because at the end we will also write xij to be greater than or equal to 0 for all the decision variables. Similar to the maximum flow and shortest path problems, we can represent this formulation on a table. And with this example, let me show you how to represent the problem on this table. Okay, so the objective function simply will be the minimization of the total cost, and the cost of arc 1, 2 is 4. 4 times x12 plus 4 times x13 plus this should be x23, 2 times x23 plus x24, 2 times x24, and then x25, it is 6 times x25, then 1 times x34, and 3 times x35, and then 2 times x45, and then 1 times x53. Okay, so this is the objective function. Now for node 1, okay, this is node 1. As I write, the right hand side, if it's a supply, it will be a positive, it will be plus 20. And the outflow, it will be positive. It is not that important even if you multiply by -1 the whole row, the result will not change. But this is just how we define, this is a convention. Okay, for node 1, x12, this is outflow, and x13, this is outflow, and this should be equal to 20. For node 2, as you can see, the net supply amount is 0, and we will write inflow, we will represent inflow as -1, similar to the shortest path, and the outflow as +1, x23, 24, and 25. For node 3, the right hand side is 0 because the net supply is 0. The inflow is x13, x23, and x53. These are all input inflow, and the outflow x34, x35. For node 4, there is a net demand, so the right hand side will be -5. Okay, the inflow x24 and x34, and the outflow is x45. And for node 5, again, there is a demand, so it will be negative 15, and the inflow x25, x35, x45, and the outflow is 1. Now the capacity constraints for all arcs, the lower bound is 0 and the upper bound for 1, 2, let me write, for 1, 2 the upper bound is 15, for 1, 3 it's 8, 2, 3 it's infinity, there is no limit, for 2, 4 it is 4, and 2, 5 it is 10, and then 3, 4, 15, 3, 5 it is 5, and then 4, 5 again there is no limit, and 5, 3 the limit is 4. And this is the final formulation. By just looking at this formulation, you can quickly write the objective function and the constraints easily. So let me write one constraint for you, how to write it. For example, for this node 4, simply we multiply the coefficient with the decision variable, so minus x24, and then minus x34, plus x45 equal to the right hand side, which is minus 5. Okay, so when I ask you to formulate a minimum cost network flow problem for a given example, it is enough to write this table. Okay, so this is all about our discussion on how to formulate the shortest path and minimum cost network flow problems as linear programs. In our next lecture, we will talk about the project scheduling and the critical path method.